Hello, everyone. We want to continue our quest to compute indefinite integrals. But now we're going to move away from basic formulas and basic properties and look into techniques of integration. And the first technique, and one of the most important one slash trickier one sometimes, is integration by substitution. The core idea of integration by substitution is that we want to integrate by making a change of variables. So you start with something really complicated, but you want to make it simpler by making a change of a variable. So I'm going to, of course, present first the technique itself, but I think the best way to truly assimilate the technique is by looking at some examples. But we're going to go over the core points of how do you integrate something using a substitution. So the first part, and this is the critical part, is to first choose part of the integral, and we're going to call that part u. And finding the right chunk of the equation and calling it u is, of course, very, very important. And here, what I've done for you is I made a little table below here of the common substitutions that we use in an integral, like what part of the equation should we choose? And I'll talk about that table in a moment. So once you've made your choice, then things become very algorithmic. So once you've chose a chunk of your equation and you call that chunk u, the first thing you do, you kind of forget about your integral, you compute its derivative, u prime. But in the notation of the technique by substitution, we're going to use du over dx. So you compute du over dx, so the chunk that you chose, the g part, you compute g prime, and then in that equation, you should see the differential term du over dx as a fraction, and you just isolate dx by simply changing the place of g prime and dx. So when you isolate dx, you get that dx is equal to du over g prime. So those are the core two elements of your substitution. So a chunk is going to be called u, and then the dx part of your integrand is going to be replaced, is going to be substituted by a du over g prime. So after that, what you do is the following. So you replace the g, the choice, by u. You replace the differential term dx by d over g prime. And then you try to simplify as much as possible your equation. And the ultimate goal is to rewrite this integral as a function of u only. We don't want to see any x's anymore. Just like in real life, we don't want to see the x's, okay? Sometimes to do that, you might need to play with your original choice, u equal gx, to have a way to get rid of the x's as an expression involving u. We'll see examples where you need that extra step. And then after that, after you simplify everything, you typically get a new integral of the form, the integral of f of u du. And then if you can't do that, that's probably because your choice is wrong. But once you have this new integral, then you apply whatever rule you need to do. Of course, ideally, after you do your substitution, you get a brand new function, and you'll see most of our examples initially will be like this, where you just need to use basic integration to get to your general indefinite integral. And then once you're done, once you apply whatever rule you need to do, you just need to replace every single u with the original function that depends on x. So if your equation starts with some x's, you are expected to give a final answer that depends on the original variable. So again, just to make it clear, the tougher part of the question is always to choose u. So what I've done here is I made a little table. This table is not exhaustive. There's other possibilities, but in a lot of those examples, the inside of a positive power is typically a good choice for u. So whatever equation you have under a power or a negative power, that's also a good attempt for the choice of u. If you have e to the power of something, or if you have an exponential function where the exponent is an equation, using that exponent is also sometimes a good choice for u. If you have sine of something, using the inside function of sine, or if you have the cosine of something, using the inside function of cosine. And actually, typically in these questions, the correct substitution is like an inner function of some function. And that's kind of the core approach, the core philosophy, the core strategy. Like, let's try to simplify this big equation because the inside is gross. Okay, so let's call this gross part just and simplify it and call it u. And then let's hope that by using the steps, we can clean it to a simpler indefinite integral. All right, let's do some examples. All right, here we go. First example, let's compute the indefinite integral of 2x times e to the power of x squared dx. So first, this is clearly not a basic integral. We have like e to the power of x squared. So as soon as you have a product, a quotient, a composition, it's unlike computing derivatives. There's no product, quotient, or chain rule. So here we have something more complicated than a basic integral. So we have to apply a technique of integration. And of course, right now, at this point, there's only one that we've seen. So of course, that one that we've seen will be the one. But in general, this can be way trickier because there's a lot of different techniques. But right now, let's try to do a u substitution. So if you think about the table that I just presented using the exponent, so here x squared as the u is going to be potentially the right strategy. And of course, there's something I like to use when I choose a substitution. Normally, I like to choose a chunk of the equation such that its derivative is next to the differential term dx. What I mean by this is that when I look at the exponent of the exponential function, which is x squared, that's a function of degree 2. And when you compute the derivative of x squared, you get 2x, which you get here exactly. And in general, as long as you get the derivative of to maybe a coefficient, you're going to be potentially on the right path for the correct substitution. So here we go. Let's try it. So let's say that the exponent here, x squared, is going to be my u. So as soon as you choose your u, right away, you compute its derivative. So the derivative of u with respect to x, and here use the differential term, the differential notation. So the derivative of u with respect to x is just going to be 2x. And now what you do, you just swap the dx and the 2x. So you isolate dx here. So you get du over dx over 2x is equal to dx. So we have a formula for x squared. That's my substitution. And we also have a formula for dx. So initially, this is kind of a, not initially, but in this question, there's kind of a double substitution. What you choose and what you compute for dx. So now my integral will become what? So we have the integral, so 2x stays 2x. The x squared is now simply u, and the dx is computed to be du over 2x. And now, of course, this is the algebraic part. You hope that you can simplify this a little bit. So here, we're very lucky. We can simplify the 2x above and below. So the 2x above with the 2x below simplifies perfectly. So what you get here, you get a brand new integral. Not a brand new, but a simplified integral. So we have the integral of eu du. So now this new integral with respect to u, so if I'm asking you just to integrate eu with respect to u, just like the integral of ex is ex plus c, then the integral of eu is just eu plus c. And the last part is to simply replace the original u, the variable u by the original equation, which is x squared. So you get that your final answer is e to the power x squared plus c. And of course, as usual, this is a very good exercise. If you take your answer and you compute its derivative, if here you just use a chain rule, the power of e to the power, the derivative of e to the power of x squared is the same thing, is going to be e to the power of x squared times the inside derivative of x squared, which is 2x. So you're getting back your 2x e to the power of x squared. All right, so that's it for the first example. All right, next example. Let's compute the indefinite integral of x cubed over 1 plus x4 dx. So again, here, not a basic integral. We have like the quotient of two things. So we need to use a technique of integration. We are in the section of substitution. So guess what? Okay, we're going to use a substitution. So here, when I'm trying to choose what part of the equation is going to be u, the only choice that I can try here is looking at the denominator. And here, again, if you use this core or this general philosophy, when I look at the denominator, I see a polynomial of degree 4, and at the numerator, I have x cubed, which is a polynomial of degree 3 next to the dx, algebraically speaking. There's a good chance that choosing the equation at the denominator, which is of course the same thing as choosing what's inside the power function where the power is -1, but this is over explaining it, is probably the right choice for you. So here we go, let's try it. So let's choose u to be the equation at the denominator, so 1 plus x4. So then right away you forget about your stupid integral, you just compute the derivative of what you just freshly chosen. So you get 1, derivative of 1 is 0, derivative of x4 is 4x cubed. Then you just isolate dx, this is just a swap here, so you get du over, over 4x cubed is equal to dx. So I have a formula for u, I have a formula for dx. So here we go. Now I just do my double substitution. So I get the integral of x cubed is untouched for now. 1 plus x4 is simplified to u, and dx is replaced by our computation, du over 4x cubed. Now you try to simplify. So, and this is more typical. Normally the simplification is not pure, but it's good enough so that you get rid of all your x's. I love substitution. All right, so here the x cubed and the x cubed simplifies. I'm still stuck with that 4 at the denominator, but to simplify this and to really see the basic integral that will emerge beautifully from this question, the over 4, I'll just kick it outside as a 1/4. And what am I left with inside? I get 1 over u du. And now, this is nice. 1 over u du, that's a basic integral with respect to u, since the integral of 1 over x is ln of absolute value of x plus c. When you integrate 1 over u du, you get the ln of absolute value of u plus c. And then the last step is always the same. Just replace u by the original equation. So you get 1/4 ln of absolute value of 1 plus x4 plus c. Technically speaking, in this example, you could remove the absolute value because 1 plus x4 is always strictly positive. But anyways, if you don't want to worry too much about it, that's the end game for that one. And again here, beautiful exercise, a joyful moment. You want to fill up your Friday nights with excitement. Compute the derivative of 1/4 ln of 1 plus x4 plus c. And then by using a chain rule, you're going to get 1/4 times 1 over 1 plus x4 times the inside derivative, which is 4x cubed, plus 0. And then everything will simplify perfectly to your original equation, x cubed over 1 plus x4. And then you know that you've done something right tonight. All right, that's it for that example. All right, the next example was initially presented as a basic formula, but actually this basic formula can be derived. I should not be using the word derive here, it might confuse you. Can be derived from an integration by substitution. So I'm going to show you where it comes from. Of course, for you guys, if you have to integrate tan, if you write ln of absolute value of secant x plus c, I'm going to be super happy, okay? But if you want to know where it comes from, because this is like part of the extended basic formulas, which are not basic at all, are just given to you. I'm just puking those out for you. But this one can actually be constructed from substitution. So anyways, so let's do it. So we have the integral of tan. Tan is, of course, by definition, sine of x over cos of x. So here I'm just using the definition of tan. So now let's do a substitution. Again here, this is very similar as the previous example. Let's try to use the denominator for u. So let's call u cos of x. So u cos of x will be replaced by u, and then right away you compute the derivative of cos to compute the derivative of u. So the derivative of cos is minus sine of x, and then you isolate dx, so it's always the same thing. You just swap the dx and the formula. So here that you just freshly computed, so here you get du over minus sine is equal to dx. So I have a formula for dx. Let me just correct, you won't see this, but let me just correct the u is gonna, here we go, du. So dx is going to be replaced by du over minus 1 sine of x. So here we go. So I have a formula for cos. It's my choice. It's u. And dx, I've computed a formula for dx. It's going to be du over minus 1 sine of x. So here we go. So here I have the integral. So sine, not part of the deal yet. Cos is simplified to u, and dx is replaced by du over minus 1 sine of x. And now simplification time. So here we go, sine and sine, bye-bye. So I can put the minus 1 outside. So for minus 1, 1 over minus 1 or minus 1, it's the same thing. So we get minus 1, the integral of 1 over u du. Now I'm back to a basic integral. The integral of 1 over u is ln of u in absolute value. So we get minus 1 ln of absolute value of u plus c. And now you replace u by its original choice, which is cos. So we get minus 1 ln of absolute value of cos. You could leave it like this, but if I want to recreate the formula here, I'm just going to use the logarithmic law, where I can take the coefficient outside of the ln and bring it up as a power. So here we go. So this is going to be the same as ln of absolute value of cos of x to the power minus 1 plus c. Power minus 1 is the same thing as 1 over. So you get ln of absolute value of 1 over cos. And 1 over cos by definition is secant. So this is where it comes from. Again here, if you just remember that the integral of tan is ln of secant, an absolute value, plus c, it's fine. If you want to reconstruct it yourself, you can do it by using substitution. Wow. I'll leave you to do as an exercise to show why the integral of cotan, it's the exact same thing. It's actually simpler because there's no minus 1 to use here. To show why the integral of cotangent of x is ln of absolute value of sine of x plus c using a substitution. All right, that's it for that example.